Hello and happy Saturday, everybody. My name's Ted, and we're making a game from scratch on a Mac. I've got my trusty microphone, I got a cup of coffee. I've actually been reviewing some of the some of the Vertex Shader code that I wrote a while back to do the transform or the coordinate transform. And I was thinking, oh gosh, this is going to be like pretty difficult to do, and how do we get the math for it? But actually, it's not that hard, and it turns out that it's not that difficult to explain. So remember, the problem that we have is I'll just run this game just so you can see. The problem we have is we want to go from what's called normalized device coordinates to what we would call more intuitive coordinates. So this is the game. This is what we've got so far. So you remember this, right? And you remember how in our list of vertices that we're going to have the GPU draw, these triangles, right? Remember how that is set up this way? So we've got like everything going from -1 to +1 on the X and Y axis. And that's what's called normalized device coordinates. If you look that up in Apple's documentation, that is ultimately what you're telling Metal, that's where you're telling Metal to draw things. So the problem though is that's not very good for gameplay logic, as I kind of illustrated in the previous video. The reason that's not good for gameplay logic is a lot of times it's much more intuitive to talk about things going from, say, maybe you have like a little rectangle for a character in your game, and that character starts at position, I don't know, he starts at position 0, and then his rectangle is defined as the position 0, 0 to, I don't know, 15, 15, right? That's a lot more easy for normal human beings to reason about. You know, my brain doesn't possess some like supercomputer where I can think in normalized device coordinates. I doubt that yours does either. So we're trying to talk about creating a more human-friendly coordinate system to represent where stuff is in our game world. With that aim in mind, I would like to present you with this equation, which we will use in our shader code. This is what I have. You see, it's outPosition dot xy. So that already should give you some indication of what kind of math we're doing here. We're doing vector math. And all that vector math is just doing the same operation on multiple data fields at the same time. It's kind of the same idea behind what you would call SIMD, or single instruction multiple data, right? So a vector is really just something where the elements are related, but you're ultimately doing the exact same calculation, just on like a wide kind of buffer of things that you're going to operate on. In this game, and in many physics simulations or models of physics, much of the physical world is modeled using vectors. So in a two-dimensional game, for example, we have the X and Y spatial coordinates. Those are actually modeled as vectors, right? So just X, Y. So what this means is this will actually go in our vertex shader. outPosition.xy, the XY vector for the position, right, equals the pixel. I call this pixel space position. What this actually is its input position. So what I mean by that is let's say that we define a point as 0, 0 from 0 to 1024, 0 to 1024. That would be one point in there. 512, 512 would be the middle of that square, right? That's the exact middle. So those are the inputs that we're going to get from our game. This input position you could say is also in game coordinates, right? You could say. So these input positions will actually be in the coordinates of our own game world. They're just going to map directly to the pixels that are on the screen. So if we define the viewport as 1024 by 1024, then that's what our actual game coordinates will be in. So keep that in mind. So then that number divided by viewport size over 2. Okay, so now viewport size, that is going to be, is a vector. So that's a vector, and it's just going to be where x is equal to 1024 and y is equal to 1024, and that's actually really important. So we vectorize the viewport, right? So we say that's just a 2-element thing where one of them is the width, the other is the height, right? And now that's divided by 2 on both sides, right? So this thing divided by 2, and then minus 1. Now this seems like a bunch of magical math, right? And you might wonder, how did we get there? But actually, if you run this, and to be honest, I didn't. You know, what I think I did is I tried to think, okay, well, you know, minus 1 on the far left extreme to, you know, 0 right in the middle, and then to 1 on that far extreme, right? So, what number in pixel space would give us 0, right? Well, that would be 512, right? And this is on, you just need to really do this for one axis. You don't even need to necessarily do them for both axes. So that's just something to consider. Right, so the middle on the x-axis is 512, right? Now, that's actually a really important number, right? That number is the same thing. And why would that be? Why is that 512? Well, that's just kind of how it is. Just like, you know, there's 1024 pixels. The middle point is 512, right? All right. So anyway, if we go here, that's actually this number right here, viewport size over 2.0, right? So that's that number. Now you take the pixel space position, so 500. So if we were in the middle, that would be 512. 512 over 512, as you can see, 505, that's equal to 1, right? Now, if we only did that part of the computation, then the resulting number would be 1, which, if we remember, our normalized device coordinates go from -1 to 1. So we need to offset that by some constant factor, right, in order to get the normalization. And that constant factor is this number right here, this -1, right? So you put it all together, and all of a sudden you start to realize that if I run this on pretty much any number inside of that range, it's actually going to result in a normalized position. So say, for example, that you know, which number is the furthest most to the left, right? Well, that number would be 0 pixels, right? Now 0 over 512, that's equal to 0, right? So 0 minus 1 equals 1, or equals -1. And just remember that -1 in our normalized device coordinates scheme is the same as furthest to the left. So now what if we try that with 1024, right? The furthest most to the right. Well, 1024 divided by 512 equals 2, right? And then 2 minus 1 equals 1, right? So that is the furthest most. So if it follows that this same calculation or computation, if it works from -1, if it works on the extremes and it works in the middle, then it doesn't take a genius to think that, hey, maybe this very exact same calculation will work on every single point in between. And in fact, it does work on every single point in between. And that's because it's done in floating point arithmetic. So you can take this equation and you can just plug it right into your vertex shader. And there you go. You've automatically got something where you can change the where your game can define the coordinate space in terms of pixels on the screen, and then with this calculation, it'll just automatically get converted over to normalized device coordinates when you run the vertex shader. So let's do that. So the first thing that we're going to do, right, we're going to open up our game. We're going to go to the shaders.metal file, right? Now the first, I already have some of this stuff kind of done already, because I've got pixel space position, right? So we get the vertex ID in, and we get the vertex array, and then we have this pixel space position, right? And all that we're going to do is this modification, right? So if we were to just do this, out.position.xy. Oops. Now you notice that we don't have viewport size here. And whether you decide to pass the viewport size or not, it's kind of up to you. Technically speaking, because we don't, because we're just kind of quickly prototyping a game inside of a small window, we can actually just hard code the value of 1024 here. So we can just do this, 1024, right? Now, there may be a strong reason why later on you might want to, pass the viewport size. One reason is if all of a sudden you want to start supporting bigger windows, you need to certainly make a note for yourself, or some kind of important note in your shader code, viewport size was not passed into the shader, the vertex shader. This will break if the game runs in any window which does not have 1024 by 1024 as its size, right? So that's just a really important thing to know. I'm not going to tell you exactly what you should support or shouldn't support. Obviously, that's kind of up to you. But it is going to be really important to make sure that you're at least aware of any possible decisions you make, where in the future, if you decide to support some other thing, it might break. And some of these are it can break in a way that's not immediately obvious, and you just don't want to be kind of chasing things. So whatever system you have to do these sorts of updates and not worry about it too much, you should have that in place. Usually though, if I leave a note here, and then the next time I'm trying, I end up looking at this, I'm oh yeah, crap, I forgot. I need to do this. Also, it's actually not that big of a deal to just pass the viewport size in, so it's not like this takes that much time to do. And it means that you could support a bunch of different things. So you could support you could support your game basically being full screen all of a sudden. You could support resizing the window, a bunch of stuff, right? And it wouldn't, really have an impact on your game logic in terms of where you tell it to draw things. But just for really quick, just to show you this working really quick, I just wanted to just hard code the number in just to show that you could do it. I think I should probably just do this as like a floating point. So we have that. And now I think I need to just change a few other things, right? So actually what I'm going to do is I'm going to just do this. I'm going to say pixel space position equals this now. Oh, no, wait. I'll define a new thing. I'll say normalized position. And that's a vector, right? So the normalized position, that's the same position, but in normalized device coordinates, right? So we're going to take that, and then the out position is just going to be the normalized position dot x and the normalized position dot y, 0, 1. So that should be fine. And then the color is going to be exactly the same. So we didn't really change much here, and what I just want to show you now is if we kept this as it is, you can imagine that it's going to have some problems, right? So first of all, if we've now defined the game coordinates, or whenever we're talking about coordinates now in the cross-platform game library, that's going to be in like pixel space, right? That's going to be in our own coordinates. So that's going to be from 0 to 1024 on the x and y axes, right? So one thing that we certainly want to do now, because this won't work, we don't have any negative, nothing can be a negative number in this scheme, right? If it's a negative number, then it's basically being drawn off of the screen, right? So that means, let's say this for example was, previously it was -1, 0, right? So the furthest most point previously was -1 on the x-axis, but now it's going to be 0, right? And now the midpoint on the y-axis is actually going to be 512, right? As you recall. And now the furthest point to the right on the x-axis is now 512, right? And the midpoint on the y is also 512, right? And now over here, the middle point on x is 512. Oh wait, oops. Actually, this is 1024. That's right. That's 1024, right? So wait, 0, 512. So this is 0, 0x, middle y, furthest away on the x, middle y, middle x, and 0y, right? And that should give us exactly the same triangle that we had before. So we'll get rid of all this. I gotta get into our Mac platform code. Oh, I gotta tell you, it feels so much nicer to like be working on this. I just spent all day yesterday on some like hairy Windows stuff. So that builds. Now let's just take a look and see if we get, the goal is to get exactly the same triangle. So if we have that, that's gonna be awesome. And we do have the same triangle. So it's the same triangle, but with one key distinction. We're now, instead of talking about normalized device coordinates, we're talking about coordinates that more closely map to the actual pixels on the screen. And that's actually going to be really nice, because what that means is we can start more intuitively reasoning about things. So one of the first things I think we're going to want to do is just start to build up some notion of, because most of the time on 2D games, right? For most two-dimensional games, you're not really ever going to you're not really going to just draw triangles. Drawing triangles is kind of more of something that you would do in a three-dimensional game, where the triangles are. So let's go back to this. You can imagine that this this triangle right here actually isn't just a triangle that you're drawing. It's like the face of a polygon, or like maybe it's like some part of someone's nose, like for a video game character, or it's a part of a cube or something like that, right? In any three-dimensional game, you would actually be drawing a lot of these triangles, which would be like polygonal faces of a 3D model that you would load it in. In a 2D game, it's a little bit different. Usually what you do is you just draw like a lot of, they're called quads. And a quad is just it's just two triangles put next to each other. So if you take two triangles, you put them next to each other, you get a square, or you get a rectangle. Why is that important? Well, because then what you can do is you can have your shader, you can have your fragment shader, your pixel shader, just like read in or output the textures from a source texture. So you can just draw a lot of these textured rectangles or textured squares all over the canvas, and that's basically how you do two-dimensional games with modern graphics programming languages, right? So, going back to this, we want to get from this to drawing some kind of a textured quad, right? And ideally, maybe what we would get to, well, maybe not, forget textured. Let's just talk about a colored quad, right? A colored quad would actually get us pretty darn far, because then what we could do is we could tell, if we had some way of saying this quad, or this basically rectangle, we're going to draw this rectangle here in this position on the screen. That's actually pretty far up the way towards having say a playable game character that you could manipulate. You could move the game character around, you could have them jump, you could have them walk around in a world. Once you got that going, then you'd be pretty far along the way towards a game, basically. Like a lot of 2D games are just moving around a rectangle. So let's move more towards that square, right? That's actually what we want to do. And we're going to do that using our game coordinates. So let's try and put a square in the middle of the screen. How would we do that? Well, let's say that the square is at, let's say it's a, just to make it easy, let's say it's a 24 by 24 pixel square, right? Simple enough. Well then, if that, if one of the, if the middle of the square, yeah, let's say that the middle of the square, I'm just going to try and draw some notes here just so I can think about this a little bit better. All right. Let's say the middle of the square is in the middle of the screen. All right. That means the furthest point on the x direction is 520, no wait, actually, yeah, it would be 512. Would it? No. It would be 524. So that would be like the x max, right? And then the x min is actually going to be, that would be 512 minus 24, which would be, if I'm not terrible at math, I think 486 pixels, right? 486. And you could do a similar thing with y. Basically, they're the same because the screen is symmetrical. So also applies to y. this is just a way of thinking about it, right? Hopefully you can see the math. This should just be like, you know, clear on its face, I suppose. Maximum is 524, minimum is 486. So if we do this, then our max x is going to be 524 here. And our, oh no, this is actually this, so this would be a point. This would be like 1 point on a triangle. So we have to take this idea and we actually have to extend it to two triangles that are put next to one another. So what we're going to do is we're going to, let's just say that we're doing the bottom triangle, right? So the question would be, what does the bottom triangle look like? Right? So if you think about it, there's going to be one of these triangles is going to be like, yeah, one of them is going to be min, right, on both the x-axis and the y-axis. And then another one's going to be max on the x, and then min on the y, right? Just a way of thinking about it. I'll just give us a little bit more space here. It's kind of fun. So yeah, let's just kind of play around with this, right? And of course, this is not going to be trying to do this in a text editor is probably not the best idea, but we shall see. So someone's going to tell me like, hey, don't do this in a text editor. This is stupid. But you can see okay, so now just kind of like pretend that this has, okay. There we go. That's actually not terrible. It doesn't look exactly like what it would look, but hey, if it helps you to think about it, right? Okay, that's actually fine. And then this point right here is actually going to be max, right? Max on the x, max on the y. Right? So that's just that. When you're first starting out with graphics languages, it's actually really important to think about this way and to break it down this way as well. Because if you don't actually just sit down and like write it on a sheet of paper or do what I'm doing here, then you'll just kind of be guessing a lot, and that sucks. So if you can start out this way, just really thinking about what are the different vertices and how do I have to compose this thing to get what I need, you just trust me, it's going to be a lot easier to work with this stuff. So we need a vertex for this one, right? So that's min, right? So that's going to be, the minimum x is going to be 486, right? So 486.0 f, you could swear, 46, right? So that's this first one. And we're not too concerned about the color that we're going to be filling in. That's not really a big deal. So just because remember, we're just trying to draw, I don't care what color this is. It could be blue or yeah, we could do the whole thing as blue. I mean, I guess why not? What did I do? Oh yeah, I tried to see. This is red, and that's green. Okay. So, oh no, that's blue. This is blue. Red, green, blue. Yeah. Okay. I just got my hotel reservation for Handmade Con because my spouse is very nice to take care of that. I'm gonna have to get going soon. hopefully we can just get this first part done, and then, yeah, that'll be it for today. I kind of want to keep these short. That's funny. All right, so we're gonna keep this relatively short. If we can just get the bottom part of this this rectangle done, you know, of course, any other YouTube person would probably shut off these shut off these messages, but I won't. You can peer into my personal life. My spouse totally pays for my hotels, and it's awesome because he gets Marriott points. So anyway, the next vertex, we've got this one right here, and so that's that one, right? And now what we need is x max, which is going to be 512, right? 512. And then y min, right? So that's going to be 486, right? All right, and then same color blue. And then just max is going to be 512 both, right? Oh no, wait, it's not 512. It's not 512. It's 524. That's right. 524 both. All right. Compile it. All right. Now let's run this thing, see what we get. Excellent. Okay, now you see that that's a fairly small triangle, but it's in the middle of the screen. And it's, I'm gonna guess that it's 24 by 24. If it wasn't 24 by 24, that would be kind of surprising to me. Now, you can see where we're going with this, right? Because the next thing that we're gonna wanna do, and I am going to have to get going after this. The next thing that we're going to want to do is just do the other, you know, the other one here. So that's going to be, no, not that. So there's this extra vertex that's like min, max, right? And then there's all the other stuff in between here, right? So there's, if you just think about it that way, you know, not the prettiest looking quad, but you get the idea. So we would just, if we're telling this that we're going to draw it as like a triangle list, then we would just, and there's, believe me, there's probably some more efficient way to do this that I'm not getting right, but you can see that the next thing we'll do in the next session, and this would actually, if you're looking for like a little activity to do on your own, figuring out how to do the rest of this quad would be a pretty darn good exercise, right? Because you're just going to have to run the math for the same for these other three vertices. Notice that two of those vertices are going to be the same, right? So you're going to have exactly the same vertices, and then you're going to have just this one is different, right? So that's definitely something to think about. Because of that, you know, excruciatingly long one that we had this week, I'm actually going to make this a fairly short video. I just think, you know, this is kind of a nice point. It kind of illustrates what I really wanted to do today, which was show you this thing right here, which is like, this is how you go from your pixel space position to normalized device coordinates all in one single calculation, one really quick calculation that you have the GPU do wide on all of the input vertices that come into it. And this just makes it really, really simple for you to work inside of your own coordinate space. Now, all of a sudden, we're actually talking about coordinates that make sense. I can easily think about what it means for a point to be at 46, 46, or 524, etc., or on some continuum from 0 to 1024. And once you have that set up, what we're going to do in the future is we're actually going to start pulling some of this stuff up into functions that we can then reuse and start to just basically draw a square of any size anywhere on the canvas, right? So we're just kind of setting up our own drawing routines. So all in all, pretty good progress today, and I look forward to seeing you next time.